I want to start today with a question that sounds, incredibly simple.
Oh, one of those.
Deceptively simple, actually. What is mass?
Okay, yeah. We are starting with the heavy hitters right away, pun intended.
Always. But seriously, if you stop someone on the street and ask them, they'd probably look at you like you're crazy and say, it's how much stuff is in an object.
Hmm.
Or maybe just, it's how much something weighs.
And for 99% of our daily lives, that's a perfectly fine answer.
Right. You buy a kilo of flour, you know what you're getting.
Sure. For grocery shopping or, packing a suitcase, that definition works. But we're looking at a paper here today by Jerry Z. Liu titled Fundamental Problems About Mass. And it basically argues that our definition of mass is, well, one of the most misunderstood concepts in all of physics.
And that's really the mission for this deep dive.
Hmm.
We are going to unpack why our two best theories of the universe, the standard model of particle physics
Yeah.
and Einstein's general relativity, are basically in a civil war
Hmm.
over what mass actually is.
It really is a bit of an identity crisis for physics. We tend to think of mass as this solid, unchanging thing, but when you look closer, that idea starts to crack.
And here's the part that really hooked me. We're going to explore this hypothesis from the source material that suggests your body's resistance to moving your inertia might actually be connected to the stars at the farthest edges of the universe.
It sounds like science fiction, but it's a real debate that goes way back. It implies that you aren't just an isolated object, you're sort of mechanically linked to the rest of the cosmos.
Wow.
But to get there, we have to do some housekeeping. We need to realize that mass isn't just one thing. It has, let's say, three distinct personalities.
Three personalities. Okay, let's break them down. So personality number one, gravitational mass.
This is the one we all feel every second of every day. Gravitational mass is, quite simply, the sensation of weight. It's what keeps your feet on the floor.
The source material uses a great example here. It mentions that even a bird instinctively understands this. It knows how to manage forces to stay in the air.
Exactly.
But we didn't really have a formula for it until Newton, right?
Right. For thousands of years, humanity was just guessing. Aristotle thought rocks fell because they wanted to go to their natural place. But Isaac Newton, he gave us the math. He defined gravitational mass in his law of universal gravitation.
The famous one, F equals G m1 middle 2 over d squared.
The iconic formula. But there's a nuance there. In that equation, mass acts like a charge.
It's like an electric charge.
Exactly. A magnet has a charge that tells you how strongly it pulls. In gravity, mass acts the same way. It's a measure of attractiveness. It tells you how strongly you pull on the Earth and how strongly the Earth pulls on you.
So gravitational mass is a relational property. It describes an interaction. It's not just about me. It's about me and the planet.
Precisely. But here's the gap in our knowledge, and the source points this out right away. We know how gravity works thanks to Einstein, but we don't really know why mass has this attractive quality.
It's the only fundamental force missing from the standard model, isn't it?
Mm.
We have particles for the other forces,
Yeah.
but no graviton.
We haven't found one. String theory proposes one, but it's still speculative. So gravitational mass is personality number one. The attractor.
Okay, let's move to personality number two. This one feels like the opposite. It doesn't attract, it resists. The loner, inertial mass.
Inertial mass. This is the stubbornness of matter. If you try to push a stalled car, it fights you. It doesn't want to move. That resistance to acceleration, that's inertial mass. Newton's second law, force equals mass times acceleration, FMA.
And the distinction the source makes is that gravitational mass feels like a relationship with the Earth, but inertial mass feels intrinsic. It's just inside the object.
Just the intuition, yeah. If you were in deep space, you'd still be hard to push. And for a long time, we just accepted that. It is what it is. But modern physics, the standard model, tries to explain why.
This is where the Higgs boson comes in.
The famous Higgs, yes. The standard model says there's a Higgs field permeating the entire universe, and the source material uses the analogy of cosmic molasses.
I love that image. So we're all swimming in invisible syrup.
Essentially, as particles move through this field, they interact with it. That interaction, that drag, gives them resistance. It gives them mass. Interact a lot, you're heavy. Don't interact at all, like a photon.
You're massless. You zip around at light speed.
Exactly.
So we have two different concepts here. One describes how hard the Earth pulls on you, gravity. The other describes how hard it is to shove you, inertia. And here's the mystery. The first big, wait a minute, moment in the source. Why are these two numbers identical?
It is strange, isn't it? If I measure a chunk of lead and it has 50 kilograms of gravitational attraction. It also has exactly 50 kilograms of inertial resistance.
Is that weird, though? Shouldn't 50 kilos just be 50 kilos?
Conceptually, not at all. They come from completely different places. One comes from interacting with the Earth, and the other, according to the Standard Model, comes from interacting with the Higgs field. Why should the molasses resistance be exactly equal to the magnetic attraction?
It's like finding out your shoe size is exactly the same as your IQ. It would be suspicious.
It's very suspicious. And physicists, including Einstein, refuse to believe it was a coincidence. Which brings us to our second segment.
Right. Einstein didn't just accept this. He built a whole theory of the universe around it.
And this leads to the famous elevator thought experiment. It's so good because it's so visual.
Okay, walk us through it.
I want you to picture this. You're in a completely sealed elevator. No windows. Soundproof.
I'm in the box. A little claustrophobic, but I'm there.
Okay, scenario B. The elevator cable snaps. You are in free fall.
Terrifying.
But what do you feel?
Well, if I'm falling at the same speed as the box, I'd float. I'd feel weightless. If I took my keys out of my pocket, they'd float right next to me.
Right. Now imagine you're just drifting in deep space, far away from any planet.
I also float. I also feel weightless.
So from inside that box, can you tell the difference between falling toward Earth and drifting in space?
No.
Yeah.
Without a window, the sensation would be identical.
Okay, scenario B. The elevator is sitting still on the ground floor. You feel gravity pulling you down.
Standards up.
Now, imagine that same elevator is in deep space, but there's a rocket strapped to the bottom. It's accelerating upward at exactly 9.8 meters per second squared.
The floor would be pushing up into my feet. I'd feel heavy.
Exactly. And the force of the floor pushing you up, your inertia resisting that push-it, feels exactly the same as gravity pulling you down. Einstein realized that if the effects are indistinguishable, the causes must be linked.
The equivalence principle.
The equivalence principle. He concluded that gravity and acceleration, gravitational mass and inertial mass are actually the same underlying reality.
And that realization is what led to general relativity.
It's the absolute bedrock. But, and here is the tension the source highlights, we still have a problem. We know that they are equivalent, but the Standard Model and general relativity don't agree on why.
And to see why they don't agree, we have to introduce the third character. We've had gravitational mass and inertial mass. Now we need effective mass.
This is where we get into the one equation everyone knows, E equals mc squared.
Energy equals mass times the speed of light squared.
Or, if you flip it around, mass equals energy divided by c squared. This tells us that mass and energy are, for all intents and purposes, synonyms. Effective mass means that the total energy of a system contributes to its mass.
The source gives some everyday examples of this. It says a hot gas is technically heavier than a cold gas.
Right, because the molecules in the hot gas are moving faster. More kinetic energy. More energy means more mass.
And a fully charged battery is heavier than a dead one.
Theoretically, yes. The potential energy stored in the chemical bonds adds a tiny bit of mass. Now, we have to be clear. For a battery, this difference is, incredibly small. Pretty much undetectable.
But there are places where this mass difference is huge, right? It's not just theory.
Oh, absolutely. In nuclear physics, we have to talk about binding energy. Think of an atomic nucleus like a structure made of Lego bricks.
Got it. My Lego tower.
The force holding those bricks together is incredibly powerful. To pull them apart, you'd have to put in a massive amount of energy. Conversely, when they snap together, they release energy.
So because they released energy to get stable, they lost mass.
Exactly. The final tower actually weighs less than the pile of loose bricks you started with. That missing mass became energy, and that measurable difference is proof that energy is mass.
So if energy is mass, does energy feel gravity?
That was the big test for Einstein. If light carries energy and energy is mass, then light should be, heavy. It should be affected by gravity.
And this leads to the solar eclipse story.
The 1919 experiment, it's legendary. So imagine a star that's physically located behind the sun. From Earth, you shouldn't be able to see it, right? The sun's in the way.
But during a solar eclipse, the moon blocks the sun's glare.
And you can see the stars around it. And what they saw was that the star was visible, but it was shifted. It wasn't where it was supposed to be.
Because the light from the star had curved around the sun.
Exactly. The sun's gravity bent the path of the light like a lens, gravitational lensing. It proved that light pure energy interacts with gravity. It has gravitational mass.
Okay, so let's recap. 1, gravitational mass and inertial mass are equivalent. 2, energy creates mass. 3, Light acts like it has mass because gravity bends it.
You've got all the pieces. Now let's smash them together and see where the physics breaks. The source calls this the conflict between the standard model and relativity.
This is the glitch in the matrix segment. The source lays out two paradoxes that really highlight the problem. Let's start with the box of light.
This one is great. Imagine a box with perfectly reflective mirrors inside. The box itself weighs 1 kilogram. Now let's pump enough light into that box photon so that the energy of that light is equivalent to 10 kilograms of mass.
Okay, so I have a 1 kilogram box and 10 kilograms worth of light energy inside. According to relativity and EMC squared, what's the total mass?
Relativity says energy is mass. So 1 plus 10 equals 11. The system has an effective mass of 11 kilograms. If you want to push that box, you have to push 11 kilograms worth of stuff.
Makes sense. But what does the standard model say?
Well, remember, the standard model says inertia comes from the Higgs field. But photons are massless. They do not interact with the Higgs field. They slide right through the molasses.
So the standard model looks at the box and sees what?
It sees the 1 kilogram box, which creates drag in the Higgs. But it ignores the photons entirely when it comes to inertia. It says the light shouldn't resist acceleration. So according to the Higgs mechanism, it should only take enough force to move 1 kilogram.
That's a huge difference. One theory says I need 11 newtons of force. The other says I need 1 newton. They can't both be right.
It's a genuine contradiction. Does the energy of the light resist motion or not? Relativity says yes. The standard model's Higgs mechanism says, I don't have a way to explain that.
That is deeply unsettling. It implies we don't know where the inertia for that light energy comes from.
It gets worse. Let's look at the second paradox the source mentions. Helium versus iron.
Okay, set this one up for us.
Imagine a chunk of solid helium and a chunk of iron. We cool them to absolute 0 to ignore heat, and we have the exact same number of protons and neutrons in both chunks.
Same building blocks, so the standard model says.
Standard model says, same particles, same interaction with the Higgs field. They should have the exact same inertial mass, same resistance to a push.
But relativity says.
Relativity looks at the binding energy. The iron nucleus is very tightly packed. The particles are bound very efficiently. They have less potential energy because they are so stable. Helium is less tightly bound, so it has higher potential energy.
And since energy equals mass.
The helium should be heavier. It should have more inertia. So again, relativity predicts a mass difference based on internal energy, while the standard model, looking only at the Higgs, predicts they should be the same.
So we have a standoff. Our best map of the particle world, the standard model, doesn't seem to account for the mass that comes from energy.
It implies the Higgs mechanism isn't the whole story. It explains the rest mass of some particles, sure, but it fails to account for the inertia we see from energy and light.
So what does this all mean? The source doesn't just leave us with a problem. It proposes a solution, a different perspective on where inertia comes from.
And to understand it, we have to go back to a philosopher named Ernst Mach. He was a huge influence on Einstein.
Mach's principle.
Right. To understand Mach, you have to look at Newton's bucket experiment. Newton spun a bucket of water. The water climbed up the sides. Newton said, aha, the water feels a force because it's rotating relative to absolute space.
But Mach asked, what is absolute space?
Exactly. Mach argued that motion is only meaningful relative to other things. He said if the bucket was the only thing in the universe, you couldn't tell if it was spinning. There would be no forces. The water wouldn't climb the sides.
So he thought the water climbs the sides because it's rotating relative to the stars.
Mass out there influences inertia here. That's the catchphrase. Mach believed your inertia is caused by the gravitational influence of all the other matter in the universe.
And this is where Jerry Z. Liu, the author of our source paper, plants his flag.
Liu argues that inertia is not an intrinsic property given by the Higgs. He suggests inertia arises from the cumulative gravitational influence of all mass distributed throughout the universe.
Wait, let me make sure I get this. When I try to push a car and it resists, that resistance is actually the gravity of all the stars and galaxies in the universe pulling on that car.
That's the hypothesis. And think about how elegant that is. We were asking earlier, why is gravitational mass equal to inertial mass? Under this theory, the answer is because they are both gravity.
That makes a lot of sense. But how does that even work? Gravity pulls things towards it. How does it stop me from moving sideways?
Think of it like a web. You are connected to every star in the universe by a tiny thread of gravity. When you're still, the tension is equal in all directions. But when you try to accelerate, when you jerk forward, you're fighting against the cumulative tension of all those threads. You are pulling against the universe.
Wow, so gravitational mass is the local gravity Earth pulling on you.
Yeah.
And inertial mass is the universal gravity, the sum of everything else in the cosmos pulling on you when you try to move.
Exactly. It unifies the concepts.
So if this is true, do we even need the Higgs field?
The source suggests the Higgs might not be necessary for generating inertial mass, or at least its role would be demoted, and it solves the box of light paradox instantly.
Because light feels gravity.
Yes. We know light interacts with gravity from the eclipse. If inertia is just the drag of universal gravity, then light automatically has inertia because it feels gravity. The contradiction just vanishes.
It really ties everything up. It takes that glitch, the fact that the standard model ignores energy mass and fixes it by saying, hey, maybe inertia isn't about the particle itself. Maybe it's about its relationship with the entire universe.
It shifts the perspective from intrinsic to relational. I don't have mass because of what I am. I have mass because of where I am in a universe full of other stuff.
That is a profound shift. It connects the very, very small to the very, very large.
It's a journey that really forces you to rethink what reality is. We think of ourselves as these independent objects, but physics suggests we are deeply tied to everything else.
Before we go, I want to leave our listeners with one final thought from the source. It's a theoretical prediction that just blew my mind.
I know the one. It's the ultimate what if.
Under this new hypothesis, that inertia comes from the gravity of all the stars. Imagine a universe that is completely empty. No stars, no galaxies, nothing. Just a single object. You.
If Mach and Lu are right, without those other stars to exert a gravitational influence, you would have no inertia.
No resistance to motion. So if you had a tiny little rocket pack, just the smallest puff of thrust,
Theoretically, you would accelerate to the speed of light instantly. With no inertia to hold you back, the laws of motion as we know them would just collapse.
you would be a ghost in the machine. It really makes you appreciate the stars, doesn't it?
Yeah.
They might be the only thing keeping us grounded.
Literally and metaphorically.
Thanks for taking this deep dive with us. We'll catch you on the next one.